So I shall begin now. Good afternoon and welcome. My name is Ruth Cameron and I'm one of the three joint heads of the Department of Materials Science and Metallurgy here in Cambridge. I took on this role in October, beginning of October this year, together with Jason Robinson and James Elliott, who are here today. And on behalf of the three of us, I'm absolutely delighted to welcome you to this, our opening event in the celebration of our centenary year. So the history of our department can be traced back to a generous donation from the worshipful company of Goldsmiths that resulted in the opening of a laboratory that was dedicated to the study of metallurgy, and that was on the 5th of October in 1920. So over the past 100 years from these beginnings, our remit has expanded, our department has flourished and grown thanks to the vision of the Goldsmiths company and also the many outstanding scientists who have worked and studied here over the years. Their achievements have made the world a better place. We really take enormous pride in our alumni, and it's absolutely fantastic that so many of you have joined us today from around the world. We're also delighted to welcome key partners from the research councils, industry sponsors, benefactors, and many other friends of the department. So, in honour of the Goldsmiths founding contribution, our discussion panel today includes three Goldsmiths professors, past and present. They and the rest of the panel will give us a flavour of how Cambridge materials research is contributing to the world now and what they see for the future. So there's going to be an opportunity for questions in the middle of our session and at the end. So please can you just type them into the chat at any point. So James will be reading these and will feed as many of them as he can into the discussions at the appropriate points. And we apologise if we're not going to be able to answer everything that comes through. We'll get through as many as we can. So your camera and your microphone is going to be switched off throughout. And just to let you know, today's session is also being recorded. So now I'm going to hand over to Professor Lindsay Greer, who's going to be chairing today's panel discussion.
Thank you very much, Ruth. It's a pleasure to convene our discussion on how material science in general, but Cambridge materials in particular, can help to save the world. Present concerns about COVID should not obscure the harsh reality that there will be no vaccine against global warming, against unsustainability, against the needs of an aging population, no vaccine against environmental degradation. In this century, material science, in our own way, convening physics, chemistry, and biology to our ends, is front and center in leading humanity out of the darkness and into the light. This month, Ruth referred to the opening of the original Goldsmiths lab on the 5th of October. This month marks our century of nurturing talent in the department, exploring fundamentals, and promoting the benefits of materials innovation. We aim today to show that by building on that history, we in Cambridge Materials, with the support of and through our alumni and partners, will not only play our part, but punch above our weight in the materials-enabled revolutions to come. If I could set the scene of a century or so ago and take us to the 30th of May, 1914, the First Lord of the Admiralty, Winston Churchill, watched as the Royal Navy's Grand Fleet left its peacetime anchorage in Portland Harbour for its war station in Scapa Flow. Churchill's description of the moonlit scene, scores of gigantic castles of steel wending their way across the shining sea, that reminds us of the imperial focus on battleships and steel. Deficiencies in British metallurgical education and research were identified before, but highlighted by World War I. The clear need to address these deficiencies was the driver for the Goldsmiths donation in 1919-1920. So it's appropriate to turn first to no less than our Tata steel professor, Harry Bhadeshia, to start our discussion.
Hello, Lindsay.
Harry, perhaps you'd like to begin by outlining some of the things the department has done in steels research.
Of course, there are many, but I think the seminal moment was when Robert Honeycomb, the late Robert Honeycomb, started the famous Steels group in Cambridge, which was characterized by real adventurous experiments and meticulous characterization of steel at many different length scales. And there were so many surprises which came out of that work. For example, the basis of interface precipitation, the theory and practice of interface precipitation, was revealed by him by direct real-time observations of step motion in the solid state using photoemission electron microscopy. And just a few years ago, there was an automotive steel invented entirely based on that science. And that steel is so mechanically homogeneous that you get a remarkable combination of formability and strength at the same time.
And Harry, you appear to be standing in the Channel Tunnel, which, even if Eurostar frequency is not what it was, can't be very safe. But
I know, but you know,
what lies behind
in your hands, I feel completely safe. So the reason for using this background is that many years ago, by studying in detail the choreography of atoms during the bainite transformation, we were able to design theoretically railway steel, which contains no carbides whatsoever. Okay, so this is the first ever carbide-free bainitic rail. It's installed in the Channel Tunnel. And in April this year, it reached 1 billion, in excess of 1 billion gross tons of traffic without any grinding that is used on normal rails to get rid of surface-initiated fatigue cracks. So this steel is very resistant to fatigue cracks, rolling contact fatigue cracks. But there's much more to it than that. The structure within consists of very fine platelets of ferrite separated by austenite. And that structure can be controlled over a very large range of length scales. So the same physics, if you like, led to the discovery of the first ever bulk nanostructured steel, which is now made into the rolling elements of some large bearings. And I believe the tie that you're wearing reflects that.
Yes, it's got Harry's steel on it, yeah.
That's right, that's right. So it's really quite exciting that the material has made it into a very safety critical application.
And Harry, what would you like to say about steels and sustainability? I can imagine that's a bit of a mixed picture, or not?
Absolutely. So, you know, I've been a metallurgist now for precisely 50 years. And during that period, there has never been a serious challenge to steels. For example, when I started, you know, the steel production in the world was about 400 million tons. It's now 1.8 billion tons. And that simply produces huge quantities of pollution. So what we need to do is to create new concepts in steels using, in particular, deep theory and creativity, so that we can reduce the total amount of steel produced while maintaining all the engineering functions. For example, you know, low density steels and austenite with affordable austenite with a low thermal expansion coefficient would make a big difference. But we need to work on this in a very dedicated manner to achieve this.
And does Cambridge provide you with any sort of special environment for doing that, do you think?
Yeah, I mean, I think there are two special things about Cambridge. The first is that with the college system, it provides a unique environment where conversations between the subjects are routine and on a daily basis. You know, so the word interdisciplinary is irrelevant. It's simply scholarship that happens in Cambridge with the environment that is provided. Secondly, you know, because of the tripod system that we have, Cambridge students don't enter the university to do a specific subject, but they can vary their direction within the first 2 years. So when they actually make a commitment to the subject, they do so on the basis of tested knowledge, okay? Detailed knowledge that they've had in the first 2 years. And what this means for us in particular in our department is that we have a strong balance of gender, of a general knowledge across the physical sciences and mathematics. And that, I think, is really spectacular when it comes to doing research of the type that we do. Materials is the most interdisciplinary subject in the world.
So that's a good point, Harry, to thank you for your contribution today, and I'll hand on to our next panelist, Louise Hirst. So Harry, sitting in the Channel Tunnel, is reminding us of improving links with Europe, but Louise shows us that the reach of Cambridge materials goes beyond the bounds of mere surface of planet Earth. So Louise, tell us a little bit about space-based services and why we should care.
Yes, certainly. So space-based services are actually already completely ubiquitous within our lives. We might not realize it, but we use them all the time. As soon as you order your Uber Eats or you look up your Google navigation, a space-based communication has taken place. And that is really set to increase in the coming years. So places where it's going to have a real impact is things like the connectivity of our energy networks, so using energy very efficiently. Also transport networks, for example, bringing online fleets of autonomous vehicles on our future roads. There's also our individual usage of data, for example, is going to be transformed by the availability, the wider availability of space-based services. And of course, the way that we use it for our emergency services is hugely enabling too. So in regions where there are natural disasters, for example, our ability to respond much more effectively. So it really is a humanitarian and economic necessity that we get this universal access to low-cost space-based services.
And your particular angle on this is getting power to devices in space?
Yeah, absolutely. So what we're working on is developing the materials and the device architectures that actually power the payloads, essentially. So that's your communication part, the power that it requires. And so these are basically photovoltaic devices, but quite different to what we would have in a terrestrial setting.
So what's your particular focus then on these new materials?
Well, some of the things that we need for space is that we need them to be particularly low mass. It costs between $5,000 and $30,000 a kilogram to launch something into space, so we need to be really efficient on that. The other unique challenge for space is radiation tolerance. So the things that we're looking at is designing materials that are intrinsically radiation tolerant, and also changing the device architectures so that they are much more able to survive in these types of environments. So for example, the current industry workhorse, if you like, that's up there powering many of our current services, that's maybe tens of microns thick. What we're looking at is designing devices that are sub 100 nanometers thick. So of course, the electronics completely changes on that length scale, as does the optics. So doing things like integrating nanophotonic structures. We're also working on developing new methods for synthesis of these materials that are better in terms of cost and also better in terms of our ability to integrate them with other materials.
Now, Louise, you're an example of somebody actually holding a joint appointment in materials and in physics. Is that a good thing or a bad thing, or what would you like to say?
Well, for me, I just came to Cambridge in 2018, and starting out and building a new group, this has been a really fantastic advantage in terms of creating new contacts and learning about the way that Cambridge runs. Specifically because my program of research is very much translational. So we are looking at really some quite fundamental concepts in optics, in condensed matter, right the way through to some very applied challenges like what's the radiation tolerance of this particular structure that we've created and can it survive a certain mission? And so having this this post, which gives me two hats and spans two departments, gives me access to a whole range of different students with different backgrounds, different experiences. And that really allows us to aim for higher impact in our research, really, particularly given its translational nature.
Well, thank you very much indeed, Louise, for that. And we'll now head back to Earth, as it were, where issues of generation of electricity without burning hydrocarbons will also play out as part of a broader aim towards an energy transition. And who better to tell us about that than our current Goldsmiths professor, Manish Chhowalla. Now, Manish, you work on atomically thin materials. I guess we've all sort of heard of graphene, but you'll tell us it's a much, much broader picture than that.
That's right, Lindsay. Thanks very much. Yeah, graphene is just the tip of the iceberg. There's hundreds of other two-dimensional or atomically thin materials. Actually, there's a long history at Cambridge on working on layered materials or intercalation compounds, as they were called in the past. But in the 50s and 60s and 70s, there was a really critical mass of research on these materials when it wasn't necessarily fashionable or Nobel Prize winning, but so we sort of picked up that mantle, and we're focusing on using these atomically thin or two-dimensional materials for enabling the energy transition. So specifically, these 2D materials have interesting properties that make them useful for generating clean hydrogen in a less polluting way. We're also looking at using two-dimensional materials for fast and rapid charging of battery electrodes that also last much longer than the typical lithium-ion battery technology. And they can also be used for low power electronics and lower energy electronics that can be integrated into new platforms such as textiles, for example. So there's a lot of interesting material science aspects to these 2D materials beyond graphene that we're investigating in a sort of fun way.
That sounds like pretty broad relevance for what we might call an energy transition. Could you say a bit about how Cambridge, well, the materials department maybe links across Cambridge in that domain and across the UK?
Yeah, that's right. So the UK was one of the first countries in the world to enact into law this energy transition, transitioning from fossil fuels to renewables by 2050 to achieve what we call the net zero carbon emission by 2050. So there's a committee on climate change. They published a report in 2008, and then the government adapted their recommendations. And so really to go from a fossil fuel based to renewable based energy generation will require real breakthroughs enabled by advances in synthesis and characterization of materials. And at Cambridge, there's a really a good critical mass of academics and researchers working across the different departments. Of course, there's a huge amount of activity in the materials department here, but there's the Sir Henry Royce Institute, which has the theme of materials for the energy transition that I direct, and we also link with Cambridge Zero as well as energy transitions at Cambridge. So there's a really vibrant community of research on this topic that's going on here at Cambridge.
And that must be a pretty broad, multidisciplinary approach.
That's right. I think the energy transition will be enabled by discovery of new materials and novel breakthroughs that really will be enabled by understanding fundamental understanding of how materials behave in non-equilibrium operating environments, for example, and really to achieve this kind of step change in energy materials performance will require an interdisciplinary approach. I think that's quite clear to academics here at Cambridge. So will require academics with complementary expertise to address fundamental technological and manufacturing challenges to enable the energy transition.
Thank you very much, Manish. It's time to move to our fourth speaker in this panel session, and then we'll head into Q&A after that. And so next we turn to Rachel Evans. And as I might say to Rachel, your elevator pitch is smart, sustainable cities. So tell us what you mean by that.
Thanks, Lindsay. Yeah, so the term smart cities originates back from the early 90s now, and it was meant to describe sort of the next generation of cities where digital technologies are used to improve the quality of life for its inhabitants. This has been expanded to include sustainable, to bring the focus really on the environmental challenges that we currently face in terms of carbon dioxide reduction, transition to renewable energies, and so on.
And your own work is targeting something particular at the moment, I guess?
Yeah, so material science can obviously contribute in a number of ways. So through the design of, energy efficient structural materials, self-healing materials, materials for carbon capture, for example, or new materials that enable digital technologies or renewable energy, for example. So our research, we work on photoactive materials. So these are materials that use light or respond to light or give out light, like the example behind me, in a measurable way. And one thing that in the context of sustainable cities, we're working on solar spectral converters, which capture sunlight and then optically concentrate it and convert it to energies that can be used more efficiently by solar cells. This is really important because actually established solar cell technologies don't really work very well in diffuse light, which is prevalent in cities. So our technology helps to boost the performance in an urban setting, essentially. So should help for expand the deployment of solar cells within cities.
Thinking of deployment, we're going to need some pretty rapid deployment of innovative technologies given the urgency of the crisis. Do you have any comments on that?
Yeah, so the average time from the lab to market for a new technology is 40 years. So given our target of carbon zero by 2050, there's clearly, we need to have an interim solution rather than the new enabling technology that's going to facilitate this. So our approach is to look at existing technologies and see how we can use materials science to either improve the efficiency or expand the functionality or utility of established technology. So in the case of solar panels, for example, that we see on our rooftops, they're placed there because they're exposed to direct sunlight. The materials we're developing can be applied directly as coatings to these established technologies to harvest diffuse light. So we can then start to think about using other surfaces within cities. So the sides of buildings, everyday objects like bus stops and seats, for example. So really designing functional architecture and expanding the utility of surfaces that are everywhere in the urban environment.
And I mean, it seems to me when you develop more sophisticated materials, that has a cost in itself. So there must be a bit of a tension between some of the sustainability issues and new technologies.
Yeah, absolutely. This is something I'm really passionate about, actually, and have been thinking a lot about how we apply this to the new materials that we're designing in our lab. So I think it's probably easier to find a solution if you're thinking about it from the outset rather than try and find a solution at the end. So we don't want to, by solving a problem, create a new one, for example. So David Attenborough obviously put plastics and polymers to the forefront, but in terms of end-of-life use and recycling. But this is actually applicable to a variety of materials. And I think we also need to be thinking about the ethics behind the materials that we're using. So we're all familiar with blood diamonds, but people might be less familiar with blood cobalt. Cobalt's an element used in lithium-ion batteries, for example, and there are concerns about how that's mined, for example.
So I'll actually cut you off there, Rachel, yeah, because actually I can see a torrent of questions coming in of a very interesting kind on our channel. So thank you very much, Rachel, for that. And we turn to James Elliott to pick a question to start with.
Hello, I'm James Elliott. I'm one of the joint heads of department along with Ruth and Jason. Thank you everyone for posting your questions so far to the chat. We only have 7 minutes for the question session, so I will have to be selective, unfortunately. I'll try to pick questions which will be open to all of the panelists. First of all, just before we begin, someone has asked how big the department has become since the 1990s. So let me just give you a quick update on that. We now actually have about 180 full-time equivalent students in the department. As you know, the students do a quarter of their year with materials in the first year, a third in the second year, and they specialize in the third and fourth years. So that is up from about between 80 and 90 full-time equivalent in the 90s. So we have more or less doubled our student numbers since then. And we have about 30 full-time staff and about 140 research fellows and postdocs. So we're in good shape at the moment. So the first question which I'd like Lindsay to put to the panel is, how are these new technologies which have been described, how are we preparing new students to leverage these technologies?
Right. I don't know who to direct that question to. Does anybody want to have a go at it? Clearly, there's a pretty general revision of our ongoing revision of our teaching provision. And it's remarkable how many things are worked in now to our Part 1A course that one would never have found there in the past. For example, biomaterials. So I think there's quite a lot going on. Rachel, would you like to comment?
Sure. Well, I think in the Part 3, so the final year of the course, it's really where we get the opportunity to sort of teach and engage the students with research activities and really bring in research-led teaching. The students also get an opportunity to undertake research projects in different labs, so they really get a hands-on experience at some of these new challenges that we're trying to find a material science solution to.
Thank you.
I think even in the undergraduate lectures, as Lindsay pointed out, we emphasize some aspects of research, but we also point out the problems associated with actually taking a material to technology. Because if you don't focus, pay some attention to that, then basically it remains as a publication.
Thank you, Harry. Back to James, perhaps.
Thank you. So someone has asked here, there's a big connection here between engineering and materials science. So can people say how we're making these new materials available for use by engineers?
I think I look directly in Harry's direction, who sees his materials in use all the time on a big scale.
Yeah, so I think we cannot do this just by ourselves. We can go somewhere along creating a new material, but then you need to spend a lot more money to prove that it can be used safely. And there's nothing better than an industrial partner to help with that. So for example, the development of this rail steel cost £17 million in the final stages of the project. And we have worked with Rolls-Royce to create a single shaft solution for civil engines. And the amount of money that Rolls-Royce spends into taking it to a certain technology readiness level is far greater than what we do in research. So without partners who are willing to take this forward, or without setting up startup companies, you have to be realistic about what can make it into the final application.
Thank you, Harry. Back to James.
Okay, so someone has asked here, have the panelists encountered anything unexpected in their research, and did that lead to new thinking, and if so, how?
Would anybody other than Harry like to jump in on that one?
Sure, I can comment on that,
Please,
Lindsay.
Manish,
Yeah, I think that's one of the sort of wonderful perks of of this job, is that we have wonderful students that discover new things almost on a daily basis. But an example in my research was that my background is in electronic materials, and when we started working with these two-dimensional materials, we're primarily interested in making better electronic devices. But a very clever student who started looking at electrochemical properties of these materials and showed that they can actually be very, very good catalysts for splitting water and generating hydrogen. And this is sort of a lateral thinking that the student tried, went with his gut instinct and tried a new experiment. And created a whole new field of research in 2013. So I think it's one of the great benefits of doing this kind of fundamental research that allows us to find unexpected results.
Thank you. Back to James.
So we have maybe a couple of related questions here. First of all, about the time from lab to commercialization. This can often be very long. How can we accelerate that? And sort of related to that, how can we deliver social and economic benefits from the research which is done?
Maybe we pick up the long time to implementation with Rachel first, because Rachel mentioned 40 years. In thinking about that, did you think of ways of shortening that 40 years?
So that comes from, there's quite an interesting study that really looks at everything that going back over the last 100 years in terms of technologies that we take into account now in everyday use. I think things are accelerating in that now research is far more interdisciplinary by its nature. So a lot of the challenges that perhaps that were encountered early on at lab stage, for example, can be sort of addressed more quickly because of this interdisciplinary nature. Of course, now we're also, from a university point of view, we're far more used to engaging with sort of thinking about commercialization and exploitation of the fundamental discoveries that we make. So, for example, engagement through Cambridge Enterprise in the Cambridge environment, for example, to license technologies out to companies, or to even spin out a company ourselves and take that forward to the next step. So there's plenty of support in the Cambridge environment, I think, that facilitates that.
And the next point, James, is essentially service to society.
That's right. Social and economic benefits of our research.
Well, I think it's hard to know where to start on that because they're so broad and diffuse. And also the point that if a company makes a new drug, it might have the name of the drug on it. We don't have the name of the materials stamped on every product that's using those materials, yet that material input might be absolutely vital. And Louise was telling us about communications, for example. I mean, that benefits all across the world, including the developing world.
Yeah, certainly. And it's, I think, something that a lot of us have actually embedded on our research really right from day one. From the moment we put pen to paper, writing a grant proposal, we're thinking about what is the ultimate impact we can have with society. And I think that lots of these grand challenges are things that material science can have a huge effect on. I mean, you mentioned several in your introduction there, Lindsay, obviously climate change, health, public health, global development. These are places where material science can have huge impacts. And I think each one of the speakers so far have highlighted how their area can do that. Certainly for me, space is that area. Yeah.
Thank you. Back to James.
So I don't know if we have time for any further questions. I think we might need to go on with the talks.
We may be able to pick up further questions in our second session at the end. So thank you, James, very much for that. We've been thinking about how the materials can help humanity move from the darkness to the light, and there's nobody who could guide us better on that than Colin Humphreys. So Colin, welcome to the screen. We naturally think of gallium nitride. Perhaps you'd like to say a little bit about its exploitation and what that can do for our world.
Right, well, thank you very much, Lindsay. And I brought along with me a bicycle lamp, which are very common in Cambridge, of course. And this is, as all bicycle lamps now, it's powered by LEDs. You can see this white LED flashing. And all white LEDs in the world are made from gallium nitride, right? You can't buy an LED in the world that's white, made from any other material. So gallium nitride is the key material for making these white LEDs. And it's really replaced other forms of lighting, like the old-fashioned light bulb or the compact fluorescent tube, very, very rapidly. And I've got a quotation here from Goldman Sachs, who wrote a pamphlet on a low-carbon economy. And they say the rapid adoption of LEDs in lighting, all made from gallium nitride, marks one of the fastest technology shifts in human history. So, you know, this new technology has come about very, very rapidly. Why are they important? They're important because they save so much energy. So Department of Energy analysis in the USA said that gallium nitride LEDs, if adopted globally, will save 15% of all the electricity produced in the world. So that's a huge saving of electricity, and of course, substantial savings of carbon emissions as well. What has prevented their use until relatively recently? That has been cost. So if you go back to 2008, it's quite hard to remember this, but a 60-watt equivalent LED would cost £50 in 2008. They were there in some parts of Buckingham Palace, but not in, you know, normal people's houses. In 2014, that £50 has shrunk to £15, and now you can buy the same LED for £3 today. So there's been a huge cost reduction. Why were they originally expensive? Because all the LEDs, the gallium nitride LEDs, were grown on 2-inch diameter sapphire wafers, which were expensive. And our group had the idea of growing them on 6-inch silicon wafers instead, which is much, much cheaper. And my postdoc, Dan Zhu, did the first 6-inch growth of gallium nitride LEDs, and that was processed in 2009, and we patented that technique.
So, Colin, that's quite remarkable. And there are whole other areas for gallium nitride as well, for example, in computing.
Yes, so it turns out, and this wasn't evident to start with, that just as gallium nitride saves a lot of energy in lighting, it's also very energy efficient in computing. So if you have a gallium nitride transistor and a silicon transistor doing the same thing, the gallium nitride consumes only 40% of the electricity of a silicon transistor. And also it operates at higher frequencies, higher power, and it lasts a lot longer. So you know, it's going to replace silicon transistors.
So if we add up the energy saving from lighting and the energy saving from computing, that's an enormous fraction of the electricity
It is
Save.
amazing, Lindsay. So the energy saving from lighting is 15%. The electricity saving from computing is 10%. And so if you add those together, gallium nitride can save 25% of our electricity consumption. So it's a most remarkable material.
Well, it's hard to beat that, I think. There's some general points about the department that we might return to those later in our discussion, Colin.
Right.
And maybe for the moment, I should make the transition to our next panelist, who's Tomayo. It keeps us with the computing theme a little bit, I think, because what Colin has told us is what materials can do for computers. Maybe Tomayo will tell us what computers can do for materials.
Absolutely. So I work in computational material science. And what that means essentially is that we try to use computers to figure out the properties of materials. And this goes all the way from macroscopic big scale materials to the atomic structure of materials. And this latter aspect is what I work on. We try to build materials one atom at a time to endow them with exotic properties that we can use them in novel technologies. And to do that, we need to solve essentially the equations of quantum mechanics. So in our own work, we work all the way from making more efficient solar cells to trying to make low power electronics for these computers that we were talking about. So another thing I want to bring up at this point is relating to the question we had about the 40-year average in going from the lab to commercialization. And that's precisely the vision of computational material science. So if we use computers to design materials virtually, we can do that much faster and much cheaper than it can be traditionally done in a normal lab. And indeed, that's the idea behind something you probably have heard about, which is the Materials Genome Project, launched in the United States a few years ago, whose motto, and I'm reading here, is to deploy advanced materials twice as fast at a fraction of the cost. So this is precisely where we can come in and help. So this is really the vision that drives our research, but there are also challenges in doing that. And the main challenge is, can we trust our calculations? Can we trust what the computer tells us that the material will behave like? And the answer actually turns out to be that not always. And just to give you an example, at the moment, we can very reliably calculate the properties of materials at the absolute zero of temperature. So that's about minus 273 degrees Celsius. However, if you want to use those materials for technological applications, that's not very useful because we want them to work at room temperature. And if we try to predict the properties of materials at room temperature, then that's much harder and the calculations are not so reliable. So that's another aspect of our research, trying to make these calculations more reliable to help us make better predictions about how materials will behave.
And as we do ever more computation and ever faster, isn't there a bit of a problem with energy consumption with this?
Absolutely. So, and this sort of takes me to a sort of a meta aspect of our research. You're absolutely correct. So current predictions are that the energy consumption coming from ICT, information and communications technology, will reach about 30% of all the energy being consumed in the world in only 10 years. So 30% of all the energy. And this includes a large fraction of this is the computer farms that power everything from Facebook to Twitter to Instagram that we use all the time, but also these very calculations that we're doing to try to design the materials of the future. So in a sense, what we're doing at the moment is we're using not so green current computers to design the greener computers of the future that will allow us to solve this problem.
Thank you for that comment. So you're relatively new to the department. Any comments from you on how you find the department?
Absolutely. So I only joined the department in January this year, so about 9 months ago. And I had spent all my academic career in physics departments, in fact. So I'm a physicist by training. So at the beginning, I was a bit worried in a sense about how I would fit in a materials department. But actually, since I've been here, I mean, it's become obvious that modern science is an increasingly, it breaks all these traditional boundaries between disciplines. So it doesn't make any more sense to talk about physics, materials, and so on. It's all very interdisciplinary. And actually, that's what I found that the materials department is all about. And I've already started collaborating with many of my colleagues to do new and exciting science. So I feel perfectly well at home in the materials department.
Well, thank you very much for that. And we'll move to our next panelist. So thank you very much, Tomayo. We're always thinking that mongrel animals might be healthier than pure breeds, but what would we say for materials? Hybrid materials come to mind, and our expert in that is our immediate emeritus Goldsmiths professor, Tony Cheatham. So Tony, you moved from UC Santa Barbara to Cambridge in 2007 to take up the Goldsmiths chair. What was it that made that move attractive? And have you any observations on the relative merits of UC Santa Barbara and Cambridge?
Yes, well, hello to everybody, and hello, Lindsay. Actually, you played an important role in moving me from Santa Barbara, which you may or may not remember, because you approached me out of the blue in 2006. And I had been thinking that I'd like to do something else before I retired. And it's always exciting to have a change of scene. And so the approach from Cambridge about becoming the next Goldsmiths professor seemed like an exciting opportunity, and I haven't regretted it for a moment, I should say. I thought the most wonderful thing about being in Cambridge, where I stayed for 10 years, was the high quality of the students and the postdocs that one could attract for research. And I think that led to probably the most productive and exciting period of my scientific career to date, anyway.
And your own research evolved in this period at Cambridge.
Yes, we had been working on hybrid materials in Santa Barbara quite a lot, though my background's in inorganic materials. And we've been working on porous metal organic frameworks. And the field had become very, very crowded, and I wanted to do something different when I moved to Cambridge. And I decided that we would explore the properties of dense metal organic frameworks rather than porous ones, sort of non-zeolitic ones, and look at their physical properties. And this turned out to be an incredibly rich opportunity. We discovered the first hybrid ferroelectrics, multiferroic materials, photoluminescent metal organic frameworks, and ionic conductors, electronic conductors, and so on. One of the highlights was actually discovering that you could make amorphous and glassy metal organic frameworks, which was done by one of my first graduate students in Cambridge, Tom Bennett, who's now in the department as a Royal Society URF. And that has turned out to be an incredibly exciting line of work with some really interesting possibilities for commercialization.
And of course, Tony, you were engaged in so many other domains while Goldsmiths professor, say at the Royal Society and looking out internationally. Anything you'd like to say about that?
Yes, actually, I became treasurer and vice president of the Royal Society. And aside from, looking over the finances, I played a very active role in developing the Society's links with the Far East, Japan and China in particular. And I also put quite a lot of effort into trying to build links between Cambridge and China. And we had a wonderful workshop with the Chinese Academy of Sciences in Cambridge. It must have been in about 2010 or 2011, something like that. And unfortunately, the university at that time decided that it didn't want to invest any further in engagement with China. And so though it got off to a good start, it really fizzled out after that.
But maybe that's something we should be picking up as we go forward.
I think so. I was thinking that, we need some kind of legacy from this centenary. And certainly one of the possible things we could do would be to have an international partnership, perhaps with university or universities in, say, China, because, that in a lot of respects is going to be an important part of our future in science and in material science.
So that might be a good idea to take out of this session that we're having now. So thank you very much for that. And I was thanking Tony, move to our fourth speaker, Malavika Near. And Malavika is going to take us further in this inorganic to organic sequence that we've met with hybrid materials all the way to Homo sapiens. So over to Malavika.
Yeah, so hi everyone. So broadly, I work in the area for regenerative devices, where the goal is to try and enable the body to repair and regenerate a version of healthy tissue at the site of injury, rather than just to replace it with permanent implants that are usually made from synthetic materials. So in order to do this successfully, we need to recruit cells, which are the building block of life, and they rely on organic materials, as we've just pointed out, and to guide them to repair the tissue as we desire. So in this sense, we are creating temporary porous structures known as scaffolds for cells to weave through and lay down new tissue during the repair process, just as we'd expect with construction scaffolds. So cells build up complex life from the bottom up, but that means that at every length scale, changes to the structure or properties of a scaffold that we create is likely to influence its behavior. So my research was focused on a multi-scale characterization of all scaffolds, all the way from the microstructure of porous networks that are templated by ice crystal growth and its sublimation afterwards, all the way down to the molecular structure of proteins that we can start to probe to look at the local and global properties of the device, such as the mechanical, biochemical, or even electrical properties. And machine learning also plays a huge part in this because of how we can now move towards data-driven models to try and predict the structures that we can get.
So it seems biomaterials has moved on a lot since peg legs for pirates.
Absolutely, yes. So peg legs for pirates and peg legs for maimed legs used to be the standard a long time ago. But then we've slowly moved towards replacements that were barely good at just providing structural support to replacements that were taking into account some of the more complex functions of the biological systems that we're trying to replicate. And today we're now really looking at regeneration rather than replacement, because as many of us maybe have encountered through various material selection charts, biological systems are incredibly complex in the number of functions that they have to satisfy. So really, we've now come to the conclusion that often the best material to replace biomaterials tend to be the biomaterials themselves.
And all of that must be highly multidisciplinary. Do you have any thoughts on how that links to our teaching program at Cambridge? Because we had an earlier question in our Q&A session of, what are we doing to prepare our students for this new world?
Absolutely. So I think one of the things, so I actually did my undergraduate at Cambridge as well, so I can also speak from that experience. So one of the most unique aspects of the Cambridge Natural Science degree is the breadth that it covers throughout the tripos and the flexibility in the earlier years to pick different disciplines within science, which I really think is about gaining exposure to various approaches to a shared problem, such as biomedical devices or biomaterials, and then later choosing to specialize in a particular approach rather than having kind of segregated areas of interest within each discipline. So having that appreciation of a variety of approaches to a problem is actually a great emulation of interdisciplinary research later down in the line. So biomaterials in and of itself is a topic that is covered in material science from the view of structure, property, processing relationships. And that's fantastic for a material science point of view, but we also have collaborations with a large variety of groups, both within Cambridge and outside, so that we can bring in their expertise into the mix and learn from them as well.
And I suppose the now quite large Cambridge Biomedical Campus is relevant here.
Absolutely, yes. So I think it must be, we have to point out that the biomedical campus are still focusing on questions that are to do with the more biochemistry aspects of problems. So they're looking at the genetics and they're looking at it from a very particular angle. So the materials department can actually bring in the fact that we are focused on it from a completely different angle and start to address problems so that we can get a more comprehensive view of the whole system rather than just looking at it from the view of cells alone.
That's very good. Thank you very much, Malavika. Launches us nicely into our next Q&A session. So I turn over to James again.
Right, thank you, Lindsay. Yes, we've had lots of questions stimulated and still some left over from the last session, but we've heard a lot about computers and artificial intelligence and machine learning and their effect on materials, also new materials for electronics. Would the panel members like to comment on how they think that's going to change the way in which material science is done in the future?
Sounds an obvious first stop for Tomayo.
Yes, more than happy to take that. It's right down my alley. So I'm a true believer in the power of computers to solve all the problems in the world. And definitely machine learning and other types of algorithms will play an increasingly important role. And just to give you a concrete example of how I see this happening, in the past few years, we've been developing new algorithms to accelerate the way in which you can calculate the properties of materials at room temperature. And it took us about 3 or 4 years to develop these new theories. And now that provides a speed up of about tenfold to previous methods. So that's what we did. But in the meantime, the hardware on which we run these algorithms has been improving by itself. So just putting this together just means that we don't get the tenfold increase just from our algorithms. We add to that the increase in hardware that are happening all the time. And I can only see that increasing. So hardware keeps getting better and better. So that means that we'll be able to do better and better calculations moving forward. So I think computation, machine learning, and otherwise will play an increasingly important role in material science.
I'm sure there's a lot more to say on that topic, but looking at the long list of questions, I think we should probably allow James to take us to the next question.
Yeah, so there have been questions about what alternatives there are to academic careers when people do PhDs. And of course, most of the people in the panel are academics, if not all of them. But could people comment on what opportunities there are for material science graduates after they've done a PhD, perhaps including outside of academia as well?
Seems to me that Tony has probably had lots of people go into not strictly academic things as well as academic positions.
Yes, I'd very much like to comment on that, Lindsay. Some of the most striking examples are people who go and start businesses, for example, startup companies. Here in Santa Barbara, we have a student who did a PhD in the Materials Research Lab. And when he finished, he started a company to explore some new polymers that he'd studied as a PhD student. And to cut a long story short, they started a company which was recently acquired for $1 billion. I mean, most extraordinary. And it's about 5 years old. Some of you might know it. They make shampoos, and it's called Olaplex. And they use very high performance polymers to make shampoos and skincare products. And so that was an extraordinary success. I've had other people who've gone into finance and into the city where, people with very good quantitative skills are highly sought after. So it's by no means the only possibility that people go into academia.
And I've certainly had people go into, dare I say, the civil service, which also has great need of people with quantitative and thinking skills. So lots of things to do. Materials can take you anywhere, I think. Back to James.
Great. Well, I think our time is rapidly coming to an end, but I'd like to just repeat a comment that's come up from the Goldsmiths, if I may. They have commented that when the Goldsmiths company set up the department 100 years ago, no one could have foreseen the incredible research that's been carried out and impacted so much of the modern work, and equally importantly, educated so many people at the highest possible level. So thank you very much for that comment. Thinking ahead to the next 100 years, does the panel have any opinions about what the department should be called in 2120?
We have, of course, gone through some name changes indeed. I think we might invite suggestions from the panel. That seems to be the modern political age. And we hope we might end up with something better than Boaty McBoatface, but perhaps suggestions from those attending would be of interest to us.
I'm not going to go there, Lindsay, because I know you like to have metallurgy in the department's name, and being one of the very few materials departments that still calls it self-materials science and metallurgy.
That, of course, is a direct link to the people who've put money in, namely the Goldsmiths company and Tata Steel. So there's a particular strong link between charitable donations to us and our topics we do and our name, but I'm sure it will still evolve.
Okay, well, maybe, do we have time for one more question? Or...
Yes, please, yeah.
Okay, so there have been some questions about the funding situation, particularly we're going through a lot of changes at the moment, political and otherwise. Do the panel members have any views about where the future funding for materials science research will come from?
If Manish is with us, would you like to comment? We
I
see
think,
our entities like
there's
the Royce Institute, for example.
That's right. So in the UK government has, at least in principle, promised to invest heavily in advanced materials and the materials discipline as a whole. And as the director of the Royce Institute here, one of the exercises that we've undertaken is to help the government identify topics for investment related to material science. I mean, the way we've done that is by engaging the UK materials community. But I think in these times of COVID and political uncertainty, we have to be reliant on many different sources of funding, not just the government.
And there, I think perhaps the materials is in quite a good position, really, to attract funds from different directions. So perhaps we head back to James at this point. Oh, Colin, you wanted to say something.
Well, I just thought it's appropriate to thank organisations like the EPSRC for their funding so far. So, I mean, my research wouldn't have got anywhere really without the EPSRC funding, and I think they've been a great funding organisation for us.
Yeah,
yes, absolutely.
Yes, indeed. James, did you want to wrap up the question?
Yes, I think Ruth would like to say a few words to wrap up the session.
You're muted, Ruth.
Thank you. The one person that didn't manage to unmute. Thank you. Looking at the questions, there seemed to be one final question that I wanted to address, which is how the department alumni can best support the progression of today's students into industrial careers versus continuing in academic research. And so I particularly wanted to pick that point up before we close. We are hugely proud of all our alumni and all of the things that they have got on to do. Indeed, there are many things that you can do to help our new students, our continuing students go into, to follow you into industry. Things like offering internships and placements for our studentships. We have a summer program that is incredibly valuable for them. Could you be a speaker for one of our speaker days? We have 3rd and 4th year speaker days where we bring in speakers from industry to share their experience. The Careers Service centrally is always looking for people to represent their work. Make sure your company is looking to recruit materials students, and promoting Cambridge Material Science at secondary school also is, as a possible course of study, is very important. And of course, finally, supporting students financially. We benefit hugely from the support that industry has provided for the research for students, and that makes a massive difference to them. So I'd like to close now by thanking our speakers and our chair for absolutely fascinating insight into the contributions of material science at Cambridge. Listening today, I'm really once again struck by the centrality of material science in tackling the world's problems and its role as a discipline bridging hub for scientific advances. And we've heard that really from as a theme running through what we've heard from many people today. So finally, thank you to everyone here for joining us today. It's been great to open our 100th year with you all present. I'm aware we haven't got to everybody's questions today, but do please feel free to get in touch with us if you'd like to continue the conversation. We're all absolutely delighted to hear from our alumni always, and we really hope to see more of you and talk with you more over the coming year. This has been the first of a number of centenary events that we're planning. We've got some ideas of our own, but we really welcome any further ideas that you have. And again, please do get in touch with us and continue the interaction with us over this year. We'll be in touch with you about further details, with further details of further events soon. So finally, thank you again.